Hello, welcome back. Today we're going to be talking about continuity. This may be a little bit of a longer video than the last ones, but it's a important topic. The definition of continuity is if you have a function f of x that has the following three properties, that at a, f of a exists at x equals a, if the limit as x approaches a, if f of x also exists, and those two things are equal, then f of x is said to be continuous at x equals a. Okay, so this is the definition, how it's usually presented in most classes. I tend to think of it really as just this equation right here, with the assumption that two things can't be equal if they don't exist. But I think the reason why they like to say this exists, therefore this, is so that students don't get like some funny idea of like maybe the limit goes towards infinity and maybe your function sort of is going to infinity, and I don't know. So just to clarify, by f of a existing, we mean f of a equals some real number. There's a point maybe at a comma L. And then this limit as x approaches a of f of x also equals L. And therefore, the two things are equal and it's continuous at x equals a. Okay, an informal definition that I like to give for when a function is continuous at a point is that the function, you can draw through it with your pen through the point at x equals a without having to lift your pen off the paper. Okay, therefore it's unbroken and therefore continuous. Okay. Let me show you a couple of ways in which a function may or may not be continuous at certain points. All right, so let's look at a couple of examples of some functions and whether or not they're continuous at certain points. Okay, the first function is going to be x squared plus 3x over x. And is this continuous at x equals 0 is my question. I just like to abbreviate the word continuous with just CONT period, because it's much quicker to write. So is this function continuous at x equals 0? Well, does f of 0 exist? If you plug in 0, you get division by 0. Therefore, f of 0 doesn't exist, so it doesn't meet all three criterions. It fails the very first one. Therefore, this function is not continuous at x equals 0. You don't even need to check the other conditions, because if any one of the three fail, then it is not continuous. Okay, another example. And this one's going to be a little bit more complicated. Okay, so it's the exact same equation as last time if x is not equal to 0. And now I'm giving it a value at x equals 0 of 3. So that fixes the first problem. If you plug in 0, we do get a value. F of 0 is 3. So it meets the first condition of continuity. Oh, I'm looking again. Is it continuous at x equals 0? So f of 0 exists. That's good. Now we need to check the limit. The limit as x approaches 0 of f of x. Now, when you're doing limits of piecewise functions, be very careful, because you're evaluating what f of x approaches as you're approaching 0 from the left or the right. In other words, for values that aren't 0, either right of 0 or left of 0. And what is our function equal to? Right of 0 or left of 0? Either way, that's not 0, so it's this function. Okay. Then we can factor out an x out of the top and cancel that with the x that's on the bottom, just leaving x plus 3. That's a polynomial, and we know for polynomials that you can just plug in the value. So if you plug in 0, you get 3. The limit exists, and it's the same as the point, f of 0, and that's the third criterion. So f of 0 existed, the limit existed, and they're both the same values. So this function is now continuous at x equals 0. So just by adding in one little point, we managed to fix the whole problem and made it continuous, which is interesting. Maybe before we continue, let's look at the original graph and this new graph to see what happened, between those two. Okay, so if we were to look at a graph of the original function, x squared plus 3x plus x, we know it's undefined at 0, and anywhere where it's not 0, these would be equal in value, and so they would cancel. And so the function is the same as just x plus 3, except we can't plug in 0. So it looks like a line, y equals x plus 3, but missing a point at x equals 0. So the graph would look like this. By the way, this is something called a removable discontinuity. A removable discontinuity is one in which the limit exists, but the point is either not the same value or the point just doesn't exist. Either way, we call it removable. I like to think of removable continuities as you can fix them if you just change one point on the graph. The point where you're trying to evaluate your continuity, either move it to the correct place where it matches the limit, or add it in if it's not there. And that's what this new function did, is it added in the point at 0, 3, filling in the hole. Now it's a continuous line. Okay, so let's look at another example. This is going to be another piecewise function. It's going to be 1 over x if x is less than 1, 2 if x is equal to 1, and 2x squared plus x if x is greater than 1. And then, is this continuous at x equals 1? Okay. So at the value of 1, we get 2. So f of 1 is 2. And this time, because I have two different functions, left of 1 and right of 1, I'm going to have to evaluate the limit from the left and the right separately, see if they're equal to see if the limit, exists in general, and finally check to see if it's 2. So let's do the limit from the left first. The limit as x approaches 1 from the left of f of x equals the limit as x approaches 1 from the left of. Now our function, left of 1 means less than 1, is the equation 1 over x. Since that's a rational function, rational functions, you can just plug in your number as long as you don't divide by 0. So we just get 1 over 1, which is 1. Now I can already see that if the right-sided limit is also 1, well, that's not going to match 2. So already I see that all three of them aren't going to be the same. But let's go ahead and look at the limit as x approaches 1 from the right, just to see how that would work. From the right means x is greater than 1. X is greater than 1 means that you use this equation. So we're going to be doing the limit as x approaches 1 from the right of 2x squared plus x. That's a polynomial, and for polynomials, you can simply plug in the number. So plug in 1 and you get 3. So because these two are not equal, the limit in general doesn't exist. And so this fails to be continuous. because the limit didn't exist at x equals 1. Okay. Also, this shows that the point and the left-handed limit and the right-sided limit can all be 3 completely different numbers, especially when you have these piecewise functions. They can make just about anything go for one of these functions. Okay. So next I want to talk about 2 special cases of functions and where they're continuous. And that is going to be polynomials and rational functions. Okay. We've already talked about this a little bit when we were talking about limits. You know, for limits of polynomials, we found out that the limit as x approaches a of any polynomial function, I'll call p of x some polynomial function, was just equal to p of a. Now, does that mean that it's continuous at x equals a? Well, polynomials, we know when you plug in a, you always get a number back out. So this is guaranteed to exist. And therefore, this is going to equal this. So if this exists, that exists, and they're both equal to the same value L. And so yes, polynomials have that property that they are continuous for all values of a. So they're continuous for all real numbers. Okay, so basically any function that has this property, is going to be continuous. That if f of a equals the limit as x approaches a of f of x, it's continuous because that's pretty much the definition of continuity. Okay, rational functions. Let me say that a rational function is a polynomial divided by another polynomial. So p of x and q of x are polynomials, okay? And when we were doing limits, once again, the limit as x approaches a of this was just equal to p of a over q of a if q of a was not 0, so that you weren't dividing by 0. So this is a little bit more complicated. These 2 things are equal as long as q of a is not 0. So what you can say is that this rational functions are continuous everywhere except when q of a is 0. Now, that means that any value of x that you plug in your denominator that makes your denominator 0, that's going to be where it's undefined, usually having vertical asymptotes there unless there's a factor on the top that cancels. But anyway, a shortcut of what you can say here is that rational functions are continuous on their domain. If you remember, the definition of a domain is it's a set of all values x that you can plug into the function that make the function defined. And the only way this is not defined is if q of a is 0. So if q of a is not 0, this doesn't work and it's not continuous. And if q of a isn't 0, this does work and it is continuous. So rational functions are continuous over their domain. And we're going to run into a whole bunch of classes of equations that are going to be continuous on their domain. In fact, a lot of your normal functions are continuous on their domain. Examples of this are going to end up being like sine and cosine are continuous over their domain, which is all real numbers. So sine and cosine are continuous everywhere. And if you've looked at a graph of sine or cosine, it's a smooth, continuous curve. You can draw through it everywhere without ever lifting your pen off the paper. So that makes sense. And we'll talk about other functions. Well, one more, like square root of x. Y equals square root of x is only defined for x greater than or equal to 0. So you can say that it's continuous over its domain. So it's continuous from 0 to infinity. Although I would have to talk about one thing, which is going to come up a little bit later, which is continuities over intervals. You have to handle the endpoints of the intervals in a little bit of a tricky way, but we'll get to that a little bit later. Okay, next I'd like to talk about the 3 different types of discontinuities. So that's going to be when a function is not continuous, You know, why is it not continuous? And what does it look like on a graph? Okay, now we've already talked about one of them, and that was a removable discontinuity. Okay, so for example, we might have this function. I'm going to define this in a piecewise function that f of x is equal to x if x is not 0 and is equal to 1 if f of x is 0. And this is a removable discontinuity. Removable, remember the way I informally said it, is that you can fix it by moving a single point, making it continuous again at that point, x equals 0. Okay. A more mathematical way of saying it is that the limit exists, but the point either doesn't exist or is just not equal to the limit. Okay, so there's nothing wrong with the limit, you know, for this type of discontinuity. It's the point that is causing the problem. Either it doesn't exist or it's just the wrong value. Either way, it's called removable. Okay, second case is going to be, what if the limit doesn't exist? Now there's going to be two different cases for this. The first case is going to be what we call a jump discontinuity. A jump discontinuity is where the function from limit from the left goes to a completely different value from the limit from the right. Something like that. Okay, so I would define this as a piecewise function. F of x equals x plus 1 if x is greater than 0 and is equal to x if x is less than 0. Oh, greater than or equal to, because I did put a solid dot over there. Okay, so jump discontinuities, it's the limit that is the problem, because the limit from the left just doesn't equal whatever the limit from the right equals. You know, both limits exist, they're just the left and the right, they're just two different values, therefore the limit in general doesn't exist. So this is a jump discontinuity. Obviously the name jump refers to the fact that if you were to try to draw through it from the left to the right, you'd have to jump up here to continue. That would require lifting your pen off the paper, which, as I said before, that's the informal definition of continuity, is you can draw through it without ever lifting your pen off the paper, which we can't in this case. So this is a jump discontinuity. Another really common example of a jump discontinuity is a special function, and this function comes up a whole lot. It seems like in UT homeworks and tests. This little function f of x equals x over the absolute value of x, and some variations on this function. Now, for any value of x bigger than 0, so let's say like 2, you'd end up getting 2 over 2, and that's equal to 1. So for any value that's positive, your function returns the value of 1, because the top and the bottom are just equal. But what if you plug in a negative number, like -2? Then the top would be -2, but the absolute value of -2 is +2. You now have -2 divided by +2, which is -1. And that happens for any negative value. The top and bottom are just equal and opposite, and they reduce to -1. So for any value of x less than 0, this is going to go to a height of -1. So we have a jump here going, you know, limit from the left is -1, limit from the right is +1. Okay, so that has a jump discontinuity. The third discontinuity is infinite, an infinite discontinuity, which refers to simply a vertical asymptote. Okay, so one example might be the function y equals 1 over x, or f of x is 1 over x. At x equals 0, we have an infinite discontinuity because you know, the limit as you approach 0 from the left is -infinity. Limit as you approach it from the right is +infinity. We use the word infinite discontinuity if either limit from the left or the right is going towards one of the two infinities, either positive or negative. So even if one side, like if this was some different function, and this side was just maybe a constant like that, I would still call that having an infinite discontinuity at x equals 0, because the limit from the right is positive infinity. Just don't worry about what the left is going to. You don't want to think of it as a jump. You can sort of say that a jump is a finite jump, not an infinite jump. Okay? Another example of a function that has an infinite discontinuity is the logarithm function. So I'll use natural log, which is log base e. ln is just an abbreviation for log base e. And that graph doesn't have values for negative numbers. And as you approach 0 from the right, it goes down towards negative infinity. So I would still say this has an infinite discontinuity at x equals 0. Okay? So these are the three different types of discontinuities, removable, jump, and infinite. There will be homework problems where they'll maybe either give you a graph or give you just a function and ask what type of discontinuity the function has. I would say probably the easiest way to do it would be to graph it. But if you really had to just do it mathematically without a graph, what I would do is I'd first look at what is the limit from the left, what is the limit from the right. If either of those are positive or negative infinity, then you're done. It's infinite discontinuity. If the limit from the left and the limit from the right exist but are not equal, like one's going to -1, one's going to +1, then you can stop and say it's a jump discontinuity. If your limit from the left and the limit from the right both exist and they're both equal, then you need to check what is the value at the point, like f of a, and if that is different, or if that point doesn't exist, then it's removable. But of course, the last case is if the point does exist and it's equal to the limit, then it's not a discontinuity at all. It's continuous at that point. And so they wouldn't ask, what type of discontinuity, or they could ask it as a broad question. They could give you a function. They could say, what is happening at x equals 2? Is the function continuous at x equals 2? Or is it a removable discontinuity? Is it a jump discontinuity? Or is it an infinite discontinuity? Because on your Quest homeworks that they give out UT, or the multiple choice tests, they like to give questions that are multiple choice like this, and so there would be 4 possible answers: continuous, removable, jump, or infinite. Okay. Next, let's talk about continuity over an interval. Okay, so first of all, I'm not sure how familiar everyone is coming into UT with interval notation. So let me briefly talk about interval notation, what it is, what it looks like. Okay, first of all, if you're trying to describe the interval from -1 to +3, like this, and we want to include the -1 but not the +3. In most classes, they would have you draw it graphically, like this on the real number line. The number 1 is -1 is a solid dot, 3 is an open circle. In interval notation, that would be an interval notation. So in interval notation, you use a square bracket when you want to include that endpoint, and you use a parentheses when you don't want to include that endpoint. Okay? So this is the same as this. If we didn't want to include the 1, if we wanted to make that also an open circle, then both sides here would be a parentheses. So you need to be a little bit careful. Whenever you see something that looks like this, you need to stop and think to yourself, is this an open interval? An open interval refers to when both sides are not included. They call that an open interval. So is this an open interval, or is it a coordinate point? You need to really read fully through the problem to make sure that we're not dealing with a coordinate point. And usually it's pretty obvious. For our class, most of the time, it's going to be an interval, because usually we're talking about like functions and the intervals on which the functions are continuous, or maybe some theorems that deal with intervals. We're usually not dealing with coordinate points, but sometimes we are, so you have to be a little bit careful with this interval notation, because the open intervals look like coordinate points. And if you wanted to include both endpoints, so if you wanted both of these to be solid, then you'd want square brackets on both sides. One last thing to mention. What if your interval went forever in one direction? Like if you wanted to describe x is greater than 2, see, which just doesn't stop, it goes to the right forever, then you would say 2 comma infinity. So just think of this as being positive infinity over here, so you're going from 2 to positive infinity. Now, infinity is not a real number, so you could never include it in the set. So you'd never have a square bracket next to an infinity, always a parentheses. And that, of course, includes negative infinity. Like, if you wanted to describe the entire real number line, you know, so that x is just any real number, it would just be the entire number line. Then it would be negative infinity, comma infinity. Both sides would be parentheses, because you can never put a square bracket next to an infinity. One last thing on interval notation. What if your solution set consists of two different parts, like x is less than 2 or x is greater than or equal to 5? How do you describe that in interval notation? Well, x is less than 2 would be negative infinity, comma 2. And I didn't want to include the number 2, so I put a parentheses after the 2. X is greater than or equal to 5 would be square bracket, 5 comma infinity, close parentheses. But how do I express the word or? These are sets. This is the set of numbers between negative infinity and 2, and that's the set of numbers between 5 and infinity. And it's not proper to put the English word or in between these two sets. Instead, we have to use a bit of set notation. It is the union symbol, which looks like a upwards U, but it doesn't have like a tail or anything like that. It's just a U like that. That is called the union of two sets. And basically the union of two sets means that your final set is anything from the first set or anything from the second set. So the union, it functionally works like the word or, but it's an operator that applies to sets. Okay? There's another operator called the intersection, but the intersection is not needed to write a final answer for an interval. So it's not as important, but the intersection would be like and it would be a upside down U like that. Anyway, like I said, it's not needed to write final answers in, so I won't talk about that anymore. Okay, so now that I've described interval notation, let's talk about continuity over an interval. Okay, first let's talk about continuity over an open interval. Remember, open intervals have parentheses on both sides, so we're not including either endpoint. Okay, and remember that that really means that x is strictly between a and b, not including a or b. So if a function is continuous over the open interval a to b, that means that it is continuous at every point x between a and b. So it's just that simple. Okay, so if a and b were the numbers 1 and 5, that would mean that our function is continuous for any number between 1 and 5, like 2 or 1.5. It would mean that if I were drawing the graph that I could draw starting from 1 and ending at 5 without lifting my pen off the paper, but with the caveat that the endpoints don't have to exist. Okay, so that's what we mean by continuous over a open interval. Okay, what about a closed interval? A closed interval, as you might suspect, is when you have square brackets. That's when you're including the endpoints. We call that a closed interval. Now, one in which one side is open and one side is closed, you know, you would just say it that way. It's not a completely open interval or completely closed, just sort of half and half. But anyway, let's describe continuity over a closed interval. Okay, so now a closed interval, we have to be a little bit careful. We're not going to say that the function is continuous for all x between a and b and including those two endpoints a and b, because we may run into some problems that way. Let me best describe this by just looking at an example, and I'll describe why it's continuous over a closed interval and what exactly that means. So let's say that we're dealing with the function f of x equals the square root of 1 minus x squared. Which looks like that. It's exactly half of a circle, the top half of a circle of radius 1. And notice you can draw from this point to this point without ever lifting your pen off the paper. Therefore, I'm going to say that it is continuous over the closed interval -1 to 1. But it's not continuous at x equals -1 or +1. Okay, so what distinguishes this from an open interval then? Okay, so a closed interval, we have to treat the endpoints a little bit separately. For a left endpoint, if you're doing a square bracket, so if you're including the left endpoint, then it needs to be continuous from the right side, which means that the limit as x approaches, let's just use that as an example. So as x approaches -1 from the right of f of x needs to equal f of -1. So this is sort of like the definition for continuity, except we're only looking at it from the right. We would say that this function needs to be continuous from the right at the left endpoint. And the function is going to need to be continuous from the left at the right endpoint. Okay? So that means that the limit as x approaches +1 from the left of f of x needs to equal f of 1. That way, the function is continuous from the right at -1 and continuous from the left at +1. These two, and all points in between -1 and 1, it's also continuous, you know, from both sides. Okay, so you know these are called sort of one-sided continuity. And it's often used when you have functions that just stop at a point and don't continue to the right of it. It's still nice to know whether or not the limit and the point are meeting, so that at the very least, you know, it's continuous from one side. Okay. So let me do one more example here. A lot of times on a homework problem, they may just ask you an open-ended question such as state the intervals, interval or intervals. There may only be one interval, there may be multiple intervals. They're not letting you know, over which the function f of x equals x over x squared minus 4 is continuous. So we're trying to state over what intervals is this function continuous. So state all of the intervals. You know, they don't want you to leave any intervals out. Okay, so let's think about this. Well, the bottom can factor into x minus 2 times x plus 2. And for rational functions, any value that makes the bottom 0 is undefined, or more specifically, if the bottom is going to 0 but the top isn't, that's a vertical asymptote. So there's vertical asymptotes at -2 and +2, but any other value it's going to be defined. And I think we had stated earlier that for rational functions, they were continuous everywhere on their domain. So, but let me sketch this real quick. Okay. -2, +2. If you plug in x equals 0, you get 0, so it's 0 in the middle. If we were to plug in +1, we would get 1 over -3, so like -1/3. If you plug in -1, you get -1 over -3 is +1/3. Okay, and then I'm just going to fake the rest of the graph. I'm pretty sure it goes like that. And then when it crosses here, it's going to come down from infinity and go to 0. Okay, there's the graph. And as you see, it's continuous over here. That's from -infinity to -2. So this is one interval where it's continuous, comma. The next interval is -2 to +2. And then comma, the next interval is 2 to infinity. No square brackets anywhere because we don't want to include the endpoints, because at -2 the function doesn't even exist, and at +2 it doesn't exist. So these would be the 3 different intervals where the function is continuous. And you don't want to use union signs in between these because you're not trying to glue them together. You're stating them as 3 separate answers. All 3 of these are intervals, you know, where the function is continuous. Okay, so this would be the answer that they're expecting for this problem. As you see, it does help to do a sketch of the problem, although, like I said, rational functions are going to be continuous over their domain. So really, it's just everywhere except these 2 points where x is either 2 or -2, where you're dividing by 0. Okay, so I think that's enough about continuity over intervals. The next topic is going to be composite functions. Okay, so you probably have heard of composite functions before in high school. I know it's taught, but I know it's easy to forget things. So a composite function is one in which you have 2 functions, and then you put one function inside of the other function. So f of g of x is an example of a composite function. And there is a special symbol for composite functions. It's a little open circle. So you would say that f circle g of x equals f of g of x. This is a composition of 2 functions. But I'm not sure if they're going to be even using this little open circle. And so let's just write it this way and stick with this notation, and, you know, instead of using that little circle for compositions. Okay, the question I have with this is, when is this limit of f of g of x, as like limit as x approaches a of f of g of x. Let's talk about when this exists. Yeah, when this exists, okay? Well, it turns out that this limit is going to equal f of the limit as x approaches a of g of x, like that, which will equal f of L, and that is, you know, if f of x is continuous at x equals L, and the limit as x approaches a of g of x is L. Okay. Whew. So, that's quite a bit. So if f is a continuous function, and g of x has a limit that's going to L, then you can pretty much replace the inside with, with what the limit is going to L, and then your answer is f of L. So let's think of an example of this to try to make some more meaning out of this. Like, what if our function f of x is a polynomial such as x squared? Polynomials are continuous everywhere, so it would meet the definition that f of x is going to be continuous at any value, because polynomials are continuous everywhere, so we don't even need to know what L is. Okay, that's great. And in the case where f of x is the function x squared, I could just write this limit like the limit as x approaches a of g of x squared equals, right? Okay. And let's assume the second thing, that the limit as x approaches a of g of x is L. Okay. And since we know that the function is continuous, because x squared is continuous everywhere, and I already stated, assume that that limit of g of x is going to L, that means that we can go from here to here, sort of factoring out the f out of the limit, like factoring the square out of the limit. And then, since we've already assumed that this is going to L, that this is going to go to L squared. Now, for people that remembered, I don't know if it was 1 or 2 videos ago, dealing with limit laws, this is simply the limit law for a function squared. So you can derive some of the laws from, from the limit laws from this, like, function squared or square root of a function. But this can do more than just reprove or, some of our old limit laws. Like, let me talk about another function that is also continuous everywhere, and that is sine. The limit as x approaches a of sine of g of x. Okay. Since sine is continuous everywhere, we can factor out the sine and then write sine of the limit as x approaches a of g of x. And then assuming that that limit is going to L, then this would just be going to sine of L. So there we have now developed a new limit law for sine. And cosine is also continuous everywhere, so you'd have a similar limit law for cosine. Okay. So that's what this composition function allows us to do, is it allows us to now do limits, outside of that, limit laws I gave you, which was a little bit limited because we only dealt with polynomials and squaring and square rooting, multiplying two functions, dividing two functions, just sort of simple mathematical operations, but we hadn't touched like sine or cosine, trig functions. We hadn't touched exponentials or logarithms. Exponentials are continuous everywhere, so they're going to have like an limit rule for exponentials. Logarithms are continuous on their domain, that is for x greater than 0, and so you would have a limit law for logarithms, at least on their domain. So this just allows us to handle all sorts of new functions, trig functions, exponentials, logarithms, hyperbolic functions, you name it. Any sort of function that is continuous, you can develop now a limit law for it. Okay, so I think I may have one example for this. Yeah, so let's use the limit law for the limit as x approaches pi of sine of x minus pi over 2. Okay. So we know that sine is a continuous function, and therefore we can factor out the sine like that. Now this is assuming that this limit exists, because if it doesn't exist, the whole thing fails. But now let's see if this exists. Well, that's a polynomial. You know, polynomials don't have to have like integer coefficients. They can have rational or real coefficients. That's fine. It's just the powers of the x have to be integers to be a polynomial. Anyway, polynomial, therefore the limit, you just plug in the number and you get the result. So it exists, and it's going to be pi minus pi over 2. So we get the sine of pi minus pi over 2, which reduces to pi over 2. And sine of pi over 2, which is 90 degrees, that's straight up, and sine is your y-coordinate on your unit circle. And so straight up, the y-coordinate would be 1. So sine of pi over 2 is 1, and that's our final answer. And we just applied that limit law for composite functions. Okay, one last thing I want to talk about, and that's going to be the intermediate value theorem. And this theorem deals with continuity, which is why we usually talk about it at this point in a textbook. Okay, so the intermediate value theorem, and forgive me, I like to abbreviate theorem with just THM. Let f be continuous over a closed interval a to b if L is between f of A and f of B, then there exists some C on the interval A to B such that f of C equals L. Okay. Once again, let's look at an example, see what this is talking about. And when you see an example, it's going to make a lot more sense. So imagine we had some sort of function that looks like this, okay? And let's say that at this point, this might be at a height of 2, and over here at this point, this might be at a height of 8, and this is at x equals 0, of course, and that this is at maybe x equals 4. Then, because my function is continuous, it's a parabola, it's smooth and unbroken, it's continuous everywhere, therefore it's continuous over the intervals 0 to 4. So A and B in this case would be 0 to 4. Okay? Now I need to pick a value of L that is in between f of A and f of B. Well, f of A is 2, or f of 0 is 2, and f of B is f of 4, which is 8. So I need to pick a value of L that's going to be between 2 and 8. So let's think of a number that's between 2 and 8, like 4. Okay? So 4 is going to be my value of L. On the graph, that might be that high. Okay? So then what this is saying is that there exists some value of C that's between 0 and 4, such that f of C equals 4. On the graph, that would be there. That is the value of C for which our function is at a height of 4. Okay? So, because the function's continuous, that means that I have to draw with my pen from here to here without lifting my pen off the paper, and therefore I have to cross a height of 4 at some point. I don't know where, I don't know the value of C, but the theorem doesn't tell you exactly where C is. The theorem just guarantees the existence of a value of C. And there could be more than one value of C, but there is at least one value of C. And the only way I could avoid hitting the number 4 is maybe if the function, maybe jumps like that, so that that's not, if the function jumps and just skips the number 4, but then it wouldn't be continuous, it'd be a jump discontinuity. Or maybe we had like a vertical asymptote, like that, but then vertical asymptote's an infinite discontinuity. So really there's no way, if the function's continuous, to avoid crossing a height that is in between these two heights. And that's why L needs to be between f of A and f of B. Okay, so that's the intermediate value theorem. Let's look at a couple of examples, and the first one's going to be like a practical example. It's going to solve a certain type of problem and using the intermediate value theorem. Okay, so let's say we have a function and we're trying to find zeros of the function. A zero of a function is where the function crosses the x-axis. So it's values where the function equals 0, like the y-coordinate equals 0. So let's look at this function right there. I know that's a polynomial, and polynomials are continuous everywhere. And that's the first thing you need to check for, is that over whatever interval you're talking, is your function continuous? And yeah, this is going to be continuous no matter what interval I state. But here's the problem. Show f of x has a 0 over the interval 0 to 1. Okay, so the first thing I'm going to note is that f of x is continuous on the interval 0 to 1 because it's a polynomial. Polynomials are continuous everywhere. Okay, next thing I want to check is what is the value of f of A and f of B. Okay, so f of 0, if we plug in 0, we get 1, positive 1. If we plug in 1 into this equation, we get 1 minus 2 minus 1 plus 1, which is 2 minus 3 is negative 1. Now the value L we're interested in, because we want to find if the function equals 0 anywhere, in other words, when is the y-coordinate 0? So 0 is the value L that we're interested in, and 0 is in between minus 1 and 1. So 0 is in between minus 1 and 1. And just as a reminder, this is the value of f of A, and this is the value of f of B, where A and B are that 0 and 1, and this 0 is the L in our equation. Okay, so I've shown the function's continuous over the interval A to B. I've shown f of A and f of B have these two values, and the L that we're interested in is in between those two values. Therefore, the intermediate value theorem kicks in and states there has to be some value of C between 0 and 1 where f of C equals 0. In other words, there is a 0 somewhere between 0 and 1. So yes, we can use the intermediate value theorem to prove that there's a 0 between 0 and 1. Note, however, I have no clue what it is. Because this would be a tricky polynomial to find that. You'd have to plug in 0 for f, and then you have a cubic equation. There is no good way to solve cubic equations, unfortunately. And so you'd be sort of stuck. Now, of course, you can go to some program like online, like Desmos, that will graph the function, and then you can see where it crosses the x-axis. Should cross it somewhere between 0 and 1, but it's probably going to be some messy number that's not going to be like 1/2 or 1/3 or anything nice like that. Okay, so this is an example of where we can use the intermediate value theorem. Let me just state that there exists some C on that interval 0 to 1 such that ST is an abbreviation for such that f of C equals 0. Sorry, that's a little bit too low. And if f of C is 0, that means that it is crossing the x-axis, and that is what we call a 0 of a function. Okay, so here is sort of a practical example, trying to find out whether a function has a 0 somewhere. And pretty much all we did was we looked at the value of f of A and f of B, and C is 0 in between these two values. That's essentially the key thing on this, as well as polynomials being continuous. Okay. Another example. What if you had the function f of x equals x over x minus 1? Note that f of 0 is equal to 0 and f of 2 is equal to 2. Does f of x equal 1 for some x on the interval 0 to 2? In other words, this problem is sort of trying to trick you to think, does the intermediate value theorem apply? Because it sort of looks like it if you just look at these things. A and B would be 0 and 2, and your f of A and f of B are also 0 and 2, and 1 is between f of A and f of B, the 0 and the 2. So by the intermediate value theorem, doesn't that mean that there's some value C, I just have x instead of C, there's some value C for which f of C equals 1 on the interval 0 to 2? Well, the problem is, the one thing we forgot to check is this function continuous over the interval 0 to 2? And the answer is no. Because when x equals 1, you have division by 0. That creates a vertical asymptote on the graph. So it is not continuous on the interval 0 to 2, which means the intermediate value theorem doesn't apply, and there may or may not be a value for which f of x equals 1 on that interval. In fact, if we were to graph it, you would see that it is not possible. Because 1 is a vertical asymptote, and it turns out that, okay, 0 is there, it's there, and I believe the graph, let's see, yeah, it goes down on this side and up on this side. This is only the part of the graph between 0 and 2, because that's all we're interested in. And as you see, the number 1 is completely missing. There's no value for which the function is equal to 1. Okay? So this is a problem where the intermediate value theorem doesn't apply because it's not continuous over the interval we're interested in, 0 to 2. Okay? And notice, just because the intermediate value theorem didn't apply, didn't mean that it couldn't equal 1 for some value. It just means we can't use the intermediate value theorem to prove it. We just have to look at the graph to see whether or not. Whereas if the intermediate value theorem is true, that means that there is some C for which f of C equals L. Even if you're not able to find it, you don't even need to graph. The intermediate value theorem is going to guarantee you're going to have some value. Okay. One last problem. So let's say that we have the function f of x equals x squared, and f of -1 is of course 1, and f of 2 is 4, right? Those are all true. Does f of x equal 1 for some x on the interval -1 to 2? I'm sorry, does f of x equal 0? That's what I'm interested in. For some value of x between -1 to 2 by the intermediate value theorem. Okay, so does the function f of x equals 0 for some value between -1 to 2 by the intermediate value theorem? You have to be really careful with this question. Notice they are not asking you, does f of x equal 0 over the interval -1 to 2? The answer is yes, because if you plug in 0 for x, you get 0 for y. So yes, f of 0 equals 0. And 0, the value of x, is between -1 to 2. But it's not because of the intermediate value theorem that this is true, okay? Because in order to use the intermediate value theorem, you know, your function has to be continuous, which it is over the interval -1 to 2. F of a and f of b have to exist, you know, 1 and 4. But here's the key thing, your value L, which is 0, has to be between f of a and f of b. 0 is not between 1 and 4. Therefore, the answer to this problem is no. You cannot apply the intermediate value theorem to prove that f of x equals 0 for some value of x between -1 to 2, even though, yes, f of x equals 0 at x equals 0. You just can't use the intermediate value theorem to prove it. So, you know, watch out for tricky questions like this. They may come up. You know, you need to test all of your conditions for the intermediate value theorem before you can, you know, jump to the conclusion that a point exists. You know, so you can't just look at a graph and go, oh yeah, a point exists where the height is 0 and it's in between -1 to 2. You can't just use that to say the intermediate value theorem told you that. Okay, so a little bit of a tricky problem, but they do like to throw in trick problems like this on the homework and the tests. So be on the watch out for that. Okay, so that's going to be it for today. Sorry if this was a little bit of a longer video than the last one, but continuity, like I said, an important topic. Yeah, one of the main reasons, I forgot to mention this, that the concept of continuity is so important is because finally we have a way to calculate limits by just applying this rule. You know, if a function f of x is continuous at x equals a, then by the third property, the limit as x approaches a of f of x has to equal f of a. So that you can just plug in a into your function and you get your answer right back out for your limit. So now this only applies to continuous functions. So if f of x is continuous on x equals a, then there is the value of the limit. You can just plug in a and you get your answer. Okay? And like I said, a lot of functions are continuous. So it turns out that like 99% of the time, in order to evaluate a limit, you simply plug in the number and that's going to be your result, assuming your function is continuous at that point, which most functions are continuous. Do be on the watch out, you know, especially if it's a piecewise function that's sort of multiple functions glued together. Then of course it may not be continuous, and you need to carefully, you know, look at your limit from the left and the right. Just do your use your limit rules regularly. Anyway, that's going to be it for today. Hope to see you next time. Have a good day.